Good morning. Hope everyone is still with energy to continue with the school. Yes? Okay, so I want to welcome Adèle and thank you for coming. Adèle is a fellow Brazilian as well, and she's done her bachelor, master, and PhD at the University of São Paulo. Has been done some work at Princeton University, at the Heart Institute of University of São Paulo, and in Columbia University, and now is in Marburg University. Did I got everything right? Yeah, okay. And then, work a lot with causal identification, causal inference, many topics into causality. So she'll show for us, give us a very good lecture, as far as I can tell from the slides so far. And so, welcome Adèle, and let's keep the energy going through these days. That should be good.
Thank you. Can you hear me? It's better, right? Yes. So again, thank you for all that are here. It's a bit hard to wake up very early on a Friday, but let's try to be awake. So the topic today is a bit introductory, but it's about how causal inference can actually move the general AI to be more explainable, generalizable, and trustworthy. Before starting, I would like you to actually go directly to the GitHub of the ProbAI, because there are two examples there, and to install the libraries, you take a lot of time, around 15 minutes. So maybe just press, start the first and second bullets there. That's for installation, and then during the introduction, probably this will be done. I will give you 2 minutes, I guess. Don't know if you need to see this. I can. So basically, the first item is to install some R packets, and then to install all the other. So this is the collab packages, and those are the other packets that we need. I guess I should do the same. So the first part is going to take very quick. It's going to be quick, but the second one is going to take around 15 minutes. And there are two examples. So if you go back to the day 5, you see the first one is the notebook BD, and then the other is notebook non-BD for backdoor and no backdoor. So if you can open both and install the libraries, it's going to be helpful. I use my example to see how much time we need. Yeah, so the first time it's done. So we can run the second part, and then start. That's done too. Then I'm running the second part. So I'm assuming that you are all with me. All right. So let's start. Sorry for this. Usually takes time to install packets. So let's start with what we know already from the field, from the machine learning and artificial intelligence field. So we know that we had several breakthroughs. For example, we can make predictions extremely well in high-dimensional settings. So this is what we have been done for maybe one decade already. In particular, we have huge progresses in reinforcement learning, computer vision, natural language processing. We have, for example, DeepMind AI algorithm that can beat the best Go player in the world. We kind of have almost, so this is still in progress, but we have driverless cars or fully autonomous cars. We have AI systems that can predict some diseases even better than human doctors. And we all know now we have GPT-4 that's being kind of exciting and scary at the same time. So a lot of progress, and it seems that we are done. Are we actually done? Do you really think that we are done? Is there anything missing? Probably you know that that's not the case, right? We don't have this, for example, we don't have explainability. So how can we make these algorithms more explainable for humans? We know that they can make predictions pretty well, but we don't know what's the reasoning behind it. So in this paper, what's the role of AI in breast cancer? I don't know how the algorithm is actually detecting breast cancer, and if we know this, we can actually make better treatments, better medications, and stuff like this. Another related topic is fairness, because once you have explainability, maybe you can decide if the process or the decision-making process is actually fair according to the rules of our society. So is actually being fair according to gender, to age, and things like that. And what actually we know is that the machine learning algorithms right now, they are having a really hard time to grasp cause and effect relationships. So what they can do pretty well is to detect associations, patterns, basically, but those patterns doesn't tell us what's the order of the variable. So where I actually have to make an intervention later to then have the effect that I would like to have. For example, for policymakers, where I should intervene later to then change the road, right? We know what are the relevant variables, but we don't know how to react to it. So that's what's the current challenge in the field. And just to summarize why causality is important. So causality has allows us some capabilities. The first capability that we are going to discuss a lot in this lecture is about effect identifiability. So how can we determine the effect of unrealized intervention? So I highlighted here this word unrealized because that's really important for us. We don't want to go to the environment, perform an intervention or like a randomized control experiment, and then observe the outcome. This would also get the causal effect for us, but it's too expensive. Sometimes it's unethical. What we want in the field is to just passively collect data. This is called observational data, and determine the effect of the outcome as if I had performed the intervention. So it's a bit ambitious, to be honest, because we have many confounders and problems in how these data are being generated in reality. But that's the goal of the field. How can we use observational data and distinguish associations or purely statistical associations to causal relationships, causation. That's the goal. And we are going to see this in this topic, effect identifiability. The second is, I mentioned already, is explainability. So why causality can give us explainability? Because we try to learn some invariances of the model that in the end are going to be interpreted as the explanation of the model. So we will see later that in the end we are not only trying to make the best prediction or trying to get the best outcome or the one that matches the observations that we have, but also we are trying at the same time to learn a model or maybe bring some prior knowledge that can help us later to enforce some type of causal relationship or explanations. Fairness, because basically explanations can lead us to fairness, and more than that, fairness is because sometimes the variable that is being used for the predictions, they are some protected, we call it protective features, but those features not necessarily are direct impacting the outcome. So this can be like an indirect process in the model, and we can actually detect what's the effect that's direct, indirect, or mediated, and confounded, and so on. Generalizability is another topic that we can see in causality. Unfortunately, I won't have time to see what there are also about that in the field. If you are interested on that, we can discuss later. But the idea is usually when you collect data, you also collect, you usually have information about the process that this data is collected. So is this from which type of population, what's the population where are collected the data, or the domain even, like could be humans or mice or pigs, can be completely different organisms, or could be different populations. But sometimes you have randomization, sometimes it's just purely observational, sometimes you have like a partial observability of the variables. So you know already in the design of the experiments how this data was collected, and causality can provide you a language to actually encode this knowledge about the design of the experiments. And then we can transport or generalize information from one domain to another in a more, in a principal way. And data fusion is exactly where it's important exactly for this type of task, where we try to combine different data sets that are coming from different populations, different domains. So how can you combine this, have a model that encodes not only the data itself, but the process that the data has been collected, to then infer causality in different domains. So I'm going to focus in the lecture in this first topic. It's already a lot of content. But we can discuss later. Of course, you see explainability, but of course you can discuss later if you're interested in the other topics. So the goal of causal data science is this, like how can we first understand the data that we have available and provide a way to combine different and heterogeneous data sets to infer causality later. And then we use this data to infer effects of intervention. So I'm going to use the same, what I mean by causal effect is the effect of an intervention. So not necessarily I perform the intervention, as I explained, but that's the goal. The causal effect is the effect after performing an intervention. And with this, we can perform more robust and generalizable decisions. That is this paper by Elias Barenboim and Adèle Pro. They wrote this in 2016, it was published in 2016. It gives you a big picture of what's the multiple goals or tasks that we have been working on in the field. And there is this website, causalfusion.net. I really recommend you if you are doing, even if you're learning, but mostly if you're trying to do research on causality, I recommend you to sign up. You can just use your academic email, and it will provide like a very intuitive tool. It's a web application where you can draw your graph, you can infer causal effects, and there are many tools that are available. I've been using this for several years already. It's been really helpful. It's not something to code, like it is just a platform where you can get intuition about the method. So I really recommend this website. So the theory that I've been talking about is by Adèle Pro. So he actually wrote this book, The Book of Why. I have to say that he was not the one that started the field, but he was the one that he brought this language that is very intuitive. That's the language of graphical models to the field of causality. So it's a way he made the field easier. That's the way that he became famous. So he won the Turing Award because of that. And this book is basically just introducing the topic for those that are just starting in the field. If you want a little bit more content or more technical results, you can also read this paper, Causal Inference, this book, Causal Inference in Statistics. It's really short, and of course it doesn't cover anything, but it's a good start. And that is the Bible. We always say that this is the Bible of causality. So if you read this whole book, probably you're going to be an expert in publishing. You'll be publishing a lot of papers just by reading this book. It's a really hard book, but at least it's a reference that you should have at home if you have, or if you are researching causality. The second book that I mentioned also has a website, the causality101.net. All the examples in the book are available in a web application here. You can kind of play a little bit, do the separation. You saw the separation in the previous lecture, in the first lecture. You see all the 4 chapters. So the book has 4 chapters. You see all the exercises implemented in the website. So it's another educational tool that you can use. I also recommend it. Okay, let's just now start with a little bit more, some technicalities. Let's see first what's the difference between prediction and effects of interventions. So in predictive tasks, we usually try to guess. So imagine this task. Can I guess how big or how serious is a fire? So imagine that you are looking at your window and you see like a big fire, and then you see a lot of firefighters trying to extinguish the fire. Can you guess how big is the fire just by looking at the number of the firefighters that are there in action? What do you think? Just guess. Like if I have like just one firefighter there, that's basically probably very small, right? But if you have 100 firefighters, probably the entire building is like on fire. So you can actually guess. You can like make a regression probably by the number of firefighters in action, the seriousness of the fire. You see a positive correlation. This is kind of obvious. So the fact that you see an association, just a statistical association, it's enough, it's sufficient to give you a good prediction. So variables that are associated to your outcome variable, those are relevant variables for prediction, just that. And this comes from a distribution that we call observational distribution. So you don't need to perform any experiment to actually have this type of intuition. You get data as it is, so from the real world, and you can actually check if the probability of y given some variable x, for example, or for example, what's the size of the fire given the number of firefighters, if this probability is different than just the probability of y. And this is the definition of association. And if this is different, of course, the x is important for the prediction of y. That's the intuition of prediction. So in conclusion, yes, the seriousness of fire increases with the number of firefighters. But the question is, so that's the conclusion, as I told you before, the fewer firefighters, the weaker the fire. Can I actually do some, can I make this question? So I know that the fewer firefighters, the weaker the fire. So if I reduce or decrease the number of firefighters, I'm going to see a decrease in the size of the fire. I'm going to reduce the fire. Of course not, right? We know by intuition that this is not the case. But why not? But the intuition here is like, can we just intervene on any variable that's associated to our outcome and expect an effect? Of course, that depends on the underlying model. So we know that in the case of the firefighters, the number of firefighters depend on the fire. So the number of firefighters is a function of the variable y. And the variable y, which is just the size of firefighters, the size of the fire, depends on other variables. We are calling u's here. So those u variables may be unobserved variables. They are the reason of why the fire is big, but the number of firefighters is not one of the reasons for the size of the fire. So the only way that we can actually see causality is to have some information about the underlying model, right? And that's what we will see later. So in this case, y is not a function of x, right? So y here is not a function of x. X is not a parameter of this function. So that's why y is not caused by x. And we will see later that one way of using the model would be just imagine that you have access to the model. If you change the equation of x to any value of x, so you go there and you change the number of firefighters. You increase, you decrease, you set to a specific number. If you change this, you won't change the value of y, but because you know that the function of y is not reacting to x. So what we will need later is actually a different type of probability distribution. So this is going to be called interventional probability distribution, which is the probability of the variables after performing an intervention on one specific variable, in the case x. And this intervention, so it's a hypothetical intervention, is going to be denoted by the operator do. So we will have this notation here for the probability of y after intervening on the variable x. And if this is just the same as the probability of y, this means now that the intervention is independent of y. So now we have a new type of reasoning that is not only about how variables are independent of other variables. Now we need to reason about how interventions or how functions of the variables, like this do x, is independent of the variable y. So in conclusion, in this example, we cannot change the seriousness of the fire by changing the number of firefighters as expected. But it's just because you know the underlying model. So what is this underlying model? So we call it this underlying model as a structure causal model, or SCM. And it is the model that provides you the full explainability for you. So if you have access to this structure causal model, you have everything. There's nothing more to do. Basically, you can just operate the functions there, see what's how one variable reacts to another, and so on. And so we assume actually that exists this model. It's going to be called data generating model. And the goal of causality is how can we infer what would be the behavior of this model, maybe without having this model. Let's see. But let's see, suppose that we have the model. And what is this model? This model is defined as a tuple with four entries here. The first entry is the variable, a set of variables v. So every time that I have a set v, you need to think this as a set of observed variables. We also call it an endogenous variable. So those are the variables that you could have access to, like you could collect the data from it. Like those are the observed variables. Of course, there are many more variables in the system that are helping or explaining some outcome. And those are going to be called exogenous variables or latent variables, or and we are going to denote as U variables. We will have a set of functions. These functions are for the observed variables. So each variable in the set V is going to be a function of other variables. So it's going to be a function of this PA. PA is just a notation for parents. And the parents are going to be a subset of the endogenous causes. So the parents are going to be the causes or the arguments of the functions of VI that are observed. Of course, we have other arguments in this function. And those arguments that are part of this set U or they are not observed, they are going to be the exogenous causes. But we need a set of functions explaining how each of the observed variable is actually determined by observed variables and unobserved variables. And we need the probability of the probability distribution over the set of variables U. In this model, we will assume that there is no cycles, so we call this model as a recursive model. This is an assumption that has been relaxed. We have some works where we show that even the theory as it is kind of capturing some of the cycles. So this is ongoing research. It's really interesting, but right now I'm going to stick with this assumption where we have no cycles. So let's see how you do how can you infer the effect of interventions in the structure causal model. So in this observational structure causal model, or before performing any intervention, we have imagine that, so suppose that this is your model. So you have two variables, just x and y. And the variable x is a function of this ux and uxy. The variable y is a function of x, also a function of another exogenous variable. It's a different exogenous variables uy, but the same exogenous variable uxy. So you imagine that you have this. If you want to compute the effect of x on y, basically you need to just replace the equation of x to any other function. Let's assume a constant. Those are called hard interventions. So I'm going to just set the variable x as a constant x. And then I can compute the value of y after this, right? I can just replace every occurrence of the variable x in my functions, and then replace to the constant x, and see how would be the value of y. So from this, so we kind of have two different roads. So we have the road where we call the observational road, and from this we have a distribution, so the induced probability distribution. From the left side here is the observational distribution. And from that probability distribution, you can do prediction. So we can get what's the best value of y after observing the value of x. So this is just association. In the other side, in the other part of the road, so it's a hypothetical road. I didn't perform the intervention. But this model also induces a probability distribution. And the type of questions that we can do now is different. So what's the best prediction for the value of y that we can make after making the intervention do x equals to x? So after making this intervention. And this interventional distribution, we can operate with it in a it is an interventional distribution, so we just operate with it in a similar way. And every time that we can see, for example, in this case, that so that's just the induced probability of the model mx. Mx is just because I did this manipulation in the model. So if in this model the probability of y is different from the probability of y in the other model, it's because the action on x is making some things, right? So actually x is a cause of y. As an example, so if you are from statistics or economics, probably you know this structural equation model. So I like to make the connection here because many people it's not that clear what's the difference between just getting this model and working with the field of with the theory of causality. So when you have a structural equation model, it is a structural causal model, but it's a very particular structural causal model where some assumptions we are making here. So we are making the assumption that the functions are linear. Okay, there are some extensions of structural equation models for non-linear, but in any case, sometimes you have to assume some type of additive, like the coefficients. It's an additive function or the noise or something. You need some type of assumption regarding to the form of the functions. Another thing is that you have to pick some distribution for the exogenous variable, so you usually assume normal distribution. Another very strong assumption for this model specifically would be, because if I say that the variables u are actually a normal distribution with a covariance matrix that's just a diagonal matrix, what I'm saying implicitly here is that I have no correlation between the variables that are explained by some external variables. So basically what I'm saying here is that I measured all the possible variables that are creating correlations or confounding across among my variables. Or in some cases, you are going to even say this assumption as being called causal sufficiency is just basically because I have all the variables necessary to explain my correlations in the data. It's a kind of a strong assumption. So, of course, if you can specify a structural equation model with like all the functions, all the specify everything, the functions, the distribution, and so on, you can just operate with it. You can just estimate coefficients. You already assume that this is the correct order of the variable, so you already have the order, you already have the causal mechanisms. So kind of there's nothing to do. It's just estimation of this model. Of course, it's hard to estimate, but the part of learning the model doesn't exist. You are assuming a model. So that's what actually try to highlight, like the knowledge that's necessary to have this the full structure causal model, to fully specify the functions and the distribution, is usually unavailable. You don't have this. So the question that he actually tried to address is it possible to identify the effect of interventions from observational data, so that's the first point, but also without fully specifying the structure causal model. So we call it in a non-parametric fashion. And yes, however, we will need some information, so I will first explain how can you do it when you have structural knowledge, and I'm going to explain what is this. So one type of relaxation of the assumptions. Sure. Yeah, I'm going to exactly formalize this, but this is just, the first slides that I'm talking about this. But yes, I'm going to require in the beginning of the presentation, I'm going to require the full specification of the causal diagram, which will be basically just the order. So what variable is what variable is an argument of the function of the order, but I'm not requiring you to say if this function is linear, if the variables that are the exogenous variables are Gaussian. I'm not going to require anything about this. So it's a relaxation exactly because I don't need to specify the form of the functions, but I still need something. And this is called the structural knowledge, right? And this is going to be encoded as a causal diagram. More questions? So how can we encode this? So this is going to be a acyclic directed that's a typo. Acyclic directed mixed graph. The M here is a mixed. So acyclic directed mixed graph. But we call it just a causal diagram. But I'm going to formalize this. So imagine that you have the structure causal model. So let's assume just for now that you have it. And this is the set of equations. The first, so to create a causal diagram, so what's the causal diagram that's induced by this model? Is we need to follow this procedure. So the first procedure is that for every variable in my set V, so for every pair Vi, Vj in my set of variables V, remember those are the sets of the variables that are observed. So for those variables that are observed, I'm going to add an edge that goes from Vi to Vj if Vi appears as an argument of the function of a Vj, right? It's simple like that. So let's assume that, let's see here. So A is a function of a UA, and UA is part of the set U. So UA is not in the first condition here. I'm not putting any edge into it because it's just about pairs of observed variables. But B is a function of A and D. So that is like an edge from A and an edge from D. C is a function from B and other U's. So I just need to add the edge from B to C, because those are the observed variables. Of course, there are the use variables. So if I was required to actually draw the entire diagram with the U variables, this would be the complete graph. So for example, the UCD appears as an argument of D and appears as an argument of C. So since it appears in both, it's pointing to D and C. The others are just appearing in their own equation. So the UA is pointing just to A, UB is just pointing to B, UD is just pointing to D, and UC is pointing to C. So it's kind of simple. But if I was to write like this diagram, it would be very complicated, not complicated, but a little bit noisy, because there are many variables. And the only variables that actually matter are the observed variables, because those are the variables that I have available. So that's why we have the second condition, that is, we only add now an edge, and this edge is going to be different. It's going to be a bidirected edge that's dashed, but this edge just represents a confounder that's unobserved. So a confounder is just a variable that points to two variables. It's just a common cause of two variables. So this is called confounder. And when it's unobserved, we call it hidden confounder or unobserved confounder. And for those variables, you need to replace or to connect the observed variables by using a bidirected edge. Right? So in this case, this is not a confounder, this is not a confounder anyways. The only confounder is the UCD. And if I move, this is going to be the only one that I need actually to draw. And for all the others that are kind of just independent of each other, I just remove it. So in the end, the process is simple. You just need to consider the observed variables. You put directed edges for those that are arguments that are just observed arguments of the functions. And for every an observed confounder, you need to add a bidirected edge. Is that clear? Okay. You saw already in the first lecture, but I'm going to repeat here. One thing that we can do on top of these causal diagrams, and maybe I should have mentioned this, a causal diagram is not only a Bayesian network. So if you induce, so this process where you induce a causal diagram from a structural causal model is actually this graph. You can think about it as a Bayesian network, but not only a Bayesian network, but a causal Bayesian network. So it not only represents the condition independencies that we have among the variables, but also the causal relationships, because I'm following the order of the true underlying model. So you need to think this as something more than just a Bayesian network, but it is also a Bayesian network. So because it's also a Bayesian network, I can use this separation to just read the implied condition independencies, right? So you saw this in the first lecture, but I'm going to define again. So to define this separation, I need a definition for a triplet that's inactive. And so a triplet is said to be inactive if either is, and it's always relative to a set Z, right? So if I have this triplet, VI, VM, and VJ, I'm going to be, and it's going to be inactive relative to a set Z, if in the set Z, the middle variable is, if the middle variable is in the set Z and is a non-collider, right? So that's one particular case. So if it's a non-collider, which means that there are no arrowheads pointing to the variable in the middle, so there is a tail in either of the edges between VI and VM or VI and VJ, then this is a non-collider. And if it is a non-collider and the variable is in the set Z, then I'm making the triplet inactive. Another way to make the triplet inactive is if the variable in the middle is a collider, and none of the descendants of such a variable is in the set Z. So I cannot have the collider, and I cannot have any of the descendants of this variable that's a collider in the set Z. We are going to see examples, but that's just the definition for inactivity of a triplet. Then we need this separation, and the separation is now, let me move here. So the separation is, we're going to require the status of a path being blocked or not, or disseparated or not. And a path is going to be disseparated or blocked, again, with respect to a set of variables z, if at least one triplet in this path, so a path is just a sequence of variables, doesn't matter what's the orientation of the edges, and it has triplets. So for every triplet, you check if one of them is if at least one of them is inactive, and if at least one of them is inactive, the entire path is inactive or blocked or disseparated. And for two variables to be disseparated, we need that every path between them every path is blocked. Let's see an example. So let's see the disseparation between x and y. So I have to check all the paths that are between x and y. The first path that's between x and y is this directed path here, x, b, w, and y. And the second path is this one through the bidirected edge, through here. So it's x, b, bidirected edge, w, and y. It's a sequence of edges, but there are two paths here. You see this, right? So you see the two paths between x and y, and I need to check if both of them are blocked, given one specific set z. So, suppose that, just ignore this, suppose that I ask you, what about the empty set, the set that has no variables on it? In this case, this path, that's directed path, is going to be open, because the first condition, so I need to check every triplet. So there are two triplets in this path, x, b, and w, and b, w, and y. The first triplet, the variable in the middle, is a non-collider, because it's not with two arrowheads pointing into B. So it's a non-collider. And since it's a non-collider, I need that the variable is in the set, because that's the way to make a triplet inactive. So the first triplet is given the empty set is open or active. The second triplet is the same, right? It's the same, is identical. So it's again a non-collider, and the variable in the middle is a non-collider, which is not in the set Z. So I have two triplets. Both triplets are active, so the entire path is active, given the set that's empty. So that's, I can already eliminate the set. The empty set doesn't disseparate because I have one path already that's active. What about the set B? If I have the variable b in the set, now I'm blocking for the path that goes from x to y through this directed path. Now I have one triplet that's going to be inactive. So this path here is already blocked. Now we need to look to the second path. In the second path, the b is a collider, but the b, since it is a collider and b is in the set, it's going to violate the second condition here for inactivity, and then this triplet is going to be active. So I'm opening this triplet. And if you look to the other triplet, is a non-collider, right? So B, W, and Y through this bidirected edge is a triplet, and the W is a non-collider. So since the W is not in the set, this triplet is active, and now both triplets are active. So this path is active given the set B, right? So it doesn't work. The set with just the W variable also doesn't work. It's exactly identical. So here we have, actually that's different. So I'm blocking the first path because this triplet here is going to be inactive. It's a non-collider. But there is a subtlety here that I would like to highlight, is that W is going to, for the second path, is going to be the descendant of the collider B. So once I use the W in the set Z, it's going to be opening this collider, because a triplet can be open if the variable is a collider And some of the descendants of such a collider is in the set. So W is a descendant, so given just W, I'm opening this collider. And I open this, but I'm blocking here. So yeah, here should be okay, right? So here should be okay because I open this B, but W here is a non-collider. So I condition on W here, and it's blocking. So it should be fine, right? I'm sorry about this. So just the W, so the first path is blocked because W is a triplet, and this is a non-collider. But it's also a non-collider in this path, and doesn't matter that this is open, because since this is open, so I have one triplet that's open, but the second triplet is blocked, is inactive, because this is a non-collider. So this would be blocked. So once I have one triplet that's inactive, the entire path is inactive. So both paths are inactive. And with B and W is the same. So I have B and W, so just W or B and W, this separates the paths between X and Y. So sorry about this. Hope you understood. Yeah. So the idea is that once we have this graph, and this graph is actually, so we have this property that's called global Markov property that we are going to, so if you actually follow the structural causal model and you induce a causal diagram, this causal diagram is going to satisfy this property, and this is going to be required later. So if you just give me a causal diagram, I'm going to require this as an assumption, which means that I'm going to expect that every disseparation in this graph is going to actually imply a condition independence in the probability distribution. So if you know the structural causal model, you induce this causal diagram, this is also this automatically satisfies the global Markov property, which means that these separations imply condition dependencies. If you just give me the causal diagram, I'm going to expect that this is satisfied. Sure.
Symbol is not deseparated?
Sure, yes. So this symbol is independence in the probability distribution, and this symbol is the same symbol for disseparation in the graph. Yeah. So we use the same notation because of this implication. It's usually expected that the probability distribution and the graph are representing the same set of condition dependencies, and it's just a way to make this clear when we operate with the graphs. Right, so that's the conclusion. The disseparations in G, they imply condition dependencies in P. G graph, P independence probability distribution. Now that you know the separation, is there any questions about this? Okay. So once you have this, you can already understand the difference between causes and predictors in a graph. So if you have a graph that explains your data or explains the data generating model, you actually can compute something that we call Markov blanket. But instead of reading the definition, which is a bit complicated, I'm going to just give you the intuition. The intuition is that everything that's connected, so imagine that I'm interested in the variable v. I want to know what's the best set of variables that predicts the variable v. So v would be my outcome, for example, in a predictive task. And I would like to know what's the best set of features that predicts this v. And the best set of features that predicts the v is the set of variables that are in a grid way associated to it. So I start with v, and then I get my neighborhood. So every variable that's connected with an edge are my neighbors. So those are my neighborhood. Those are obviously associated to v. However, once I condition on my set of neighbors, I can open some colliders. Using the separation, you know this already. So, for example, here, the v, I have v, this variable, and the other variable. This forms a a triplet where the variable in the middle is a collider. So conditioning on this variable, I actually have a association to this third variable here, because I open this triplet. So it's in a grid way. I compute the set of neighbors, I condition on the neighbor, and then I check every variable that's associated by a bidirected path. So this is a bidirected path, or actually a path where the variables in the middle are colliders, and then this variable is going to be, this triplet is going to be active, and then this is going to be associated to V. It's the same for like if I have bidirected edges. So in this case, you see once I condition on this variable, once I use this variable in my set for this separation, V is not going to be disseparated to this variable. It's going to be deconnected. So, and then I have like a larger region of variables that are connected to V. So every variable that I can include that's creating association to V are going to help my prediction. And I can keep this process until like I don't have anymore a open triplet. So in this case here, I actually can condition on this, and this will be associated. But once I condition on this variable, now this triplet is a non-collider. So this is no longer associated to V. So this is not going to be relevant for prediction. But in this other sequence here of nodes, I will condition on this, then this is going to be associated. So I condition on this again, this is going to be associated. And this can be very far. And you see that those are not causes. Like the path, if you see that there is no directed path going from one variable, from this variable to the V. The only causes are those in red. The causes are those that are having a directed path that goes to V. So the first two, the neighbors that have a directed edge, they are direct causes, but there are other variables that are indirect causes that could actually have an influence on V if you're interested in indirect causes. And they not necessarily are going to be dependent of the variable. For example, this white with a border, red border, is a variable that's not even associated to V, but it is an indirected cause. The set of directed causes is always a subset of the Markov blanket. So Markov blanket is just the ones in gray. That are the variables that are associated to V. But the causes are those that have directed paths from the variable to the variable V. So this is already help us to understand why we cannot just get the set of variables that help my prediction and assume that they are all causes. To be honest, there are just a few of them that are actually causes. Many variables are just spuriously associated, we call it. Questions? Oh, I'm a bit late. So just I need to conclude this, unfortunately. Let me conclude this part. So when we do a randomized experiment, we actually do the following. So we randomize, so we imagine that there are many confounders between an association between X and Y. And this would be a representation of my road. Like this variable U can represent many variables. So when I do a controlled experiment, a randomized controlled experiment, I can actually go in the environment and randomize the variable X. And when I do this, what I do actually, I minimize the influence of any variable that's affecting X. And just and then what in the graph this would represent like as if I'm removing the edges that are into the variable X. So I'm removing everything that's creating a confounder. Remember that confounder are those variables that are pointing to X and Y at the same time. And when I do a randomized control experiment or randomized control trial, I kind of simulate the idea of cutting the influence of these confounders. So that's why we can actually get the effect, the causal effect of X and Y. So from the graph, we can actually have the interventional graph. And this graph is called GX bar because we just cut the variables into X. And basically, from the graph, we have a way to operate on this. I can, should I stop? It's almost 1 hour. Maybe I should give you 10 minutes just as a break. I don't know. Yeah? All right. Let's take a break. Then I finish this part, and then we can do the exercise. So I want to now start with something that Pro actually showed in his book, of the Book of Why. It's something that we call Pro's causal hierarchy, or Pro's inferential hierarchy, that shows that actually there are 3 types of inferences in the field. The first one is about statistical associations. That's the type of inference that we are used to do it. Then the interventional inferences, or the causal inferences, are the ones that are that we call it, this is in the second layer, and then there's the third layer that we're going to see. It's called counterfactual. These 3 types of inferences, they would be able to, you would be able to do it directly from the structural causal model, because this is just the most complete information that you have from the environment. But every time that you don't have the complete graph, you have some type of loss of information. So just the graph, the observation of the graph, the one that we induced using that procedure, it's not encoding all the information of the structural causal model. We saw that. It's just the structure. The same happens with the observational distribution. So the information that's available in the observational distribution is not even what we cannot actually have from the causal diagram. It's just about dependencies and independencies, conditional, but dependencies and independencies. And then actually you can estimate this from data. So every time that you move from the structural causal model to something that is induced from it, you have some loss of information. And the same happens in the interventional causal diagram, in the interventional SEM. If you have the interventional SEM, you can do much more than if you just have the graph, the interventional graph, or the interventional distribution, or just the interventional data. And because of this loss of information, we have something that that defines this layer. So just let me conclude. Let me make this more clear. So from the reality that could be observational or interventional, you see that the difference is, the only difference between the 2 roads is the fact that in the first one, X is reacting to the natural behavior or the natural functions, and the second one, X is fixed through randomization, or maybe through any other intervention, but it's different than the one from the reality. And those models, they induce the causal diagram, so you could, from both in the both roads, you could induce the causal diagram. And in most applications, the problem is like we only have data, right? So that's even some questions that came up during the break. Like, what happens if I have no knowledge and I have just data? Can I just try to infer causal effects from it? So from data, imagine that I don't have any type of data that comes from an experiment. So from data, we can, for example, fit a neural network and try to estimate the best probability distribution of Y given X, right? So we can do this already. But this is in the observational world. And as I tried to explain before, this observational distribution is really helpful for prediction. So you can do predictions pretty well, as we can see in many of these breakthroughs in the field. But the goal here is, like, can you move from data from this observational distribution here and infer the interventional distribution where I don't actually have any information about the road in the bottom here. So how can I move from this reality where I just observe, where I just see the behavior of the variables, to this other world where I'm doing or performing intervention? How can I do this? The problem is when I have just data, is the same data. So this is a result. Like the same data can be used to infer observational distribution, but this observational distribution could be explained by different graphs. So those are called Bayesian networks. So I actually could draw many graphs that can perfectly explain our observational distribution, because the only thing that I need to represent in those diagrams are a set of conditional dependencies and independencies, mostly independencies. So doesn't matter what's the direction of the edges, as long as I'm representing those associations and these dependencies and independencies in the data, I'm fully representing this observational distribution. And deciding which of those are the true one is something that it's impossible, like unless you make some assumptions. And more than that, like each of these diagrams, so this could be the true one, suppose, but each of these diagrams actually can actually be the graph that was induced by many structural causal models, because I can just change the functions, and as long as I'm respecting the order or the edges, the structure that is represented in this graph, those are compatible with my diagram. So the diagram per se is already a class of many models. And the data in the end can be actually represented by many, many, many models. Like, how can I actually go there and pick one and say, this is the true one? If all of those can perfectly, I'm not saying that it's a result, like all of those could represent perfectly the observational distribution, at least in terms of dependencies and independencies. And even if you make assumptions, so in one assumption in the field is the one that I told you, like it's about causal sufficiency, where you don't have unmeasured confounders, so you don't have these bidirected edges here. And those models, we call it Markovian models. But even in those models, if you make this assumption where you don't have unobserved confounders, you still have multiple models that could fit your data. And that's the problem. Like when you just pick one, let's try to fit a neural network to the data. Many could be the one in the end, the one that the machine learning actually decided to fit. So you cannot assume, you cannot assume that the output of your machine learning model is the one that has the causal explanations that actually generated the data. You can fit like a deep generative model and start sampling from it. Those samples are not exactly those, maybe if you're very lucky and you could actually pick the true one, but there is like a very high chance that this is just one of the models of this entire class, and doesn't matter what you're getting there. You see in the end, like you can see the correct distribution, so you can see the correct, this is going to predict perfectly the observational distribution, but the explanations not necessarily are the true ones. Your question?
Is there some kind of ground truth like this for causality, or do we say we have
the goal is actually to infer the causal effect. So we have to make a few assumptions. So if you want, you can assume the model. You can even, like, let's write the equations and assume that this is my model, I'm done. Is kind of strong as well. Like, let's just pick one model, let's assume that this true one, and let's compute the effect. So as long every assumption that you are doing is actually correct, if you don't violate those assumptions, in the end, this is the causal effect. So as in any technique, if you violate the assumptions, you cannot trust the output. Of course, the goal here is to relax these assumptions. So maybe in the end, you will see later that there are some techniques that can actually help you to not pick the fully graph. But the point that I want to make here is that don't imagine that just feeding a neural network you can have 100% of accuracy in your classification. You can like generate very good samples that mimic equally, mimic perfectly your distribution. Don't trust that this is the true causal model and try to see, like if you make an intervention in this model, see that expect that this is going to be the effect in the real world, because it's just one of the models. That's just the point of this slide. More questions? And that's why we have the ladder of causation. Like in the ladder of causation, we have the 3 layers. The first layer is the observational one. So in this case, you can answer this type of question. So it's about prediction. So and you can use all these machine learning models that we are used to use. Like the questions would be, how would seeing X change my belief in Y? So what does a symptom tell me about a disease? I'm just guessing. It's just like there is a chance, like after observing a variable, you predict some other. But this doesn't mean that that variable is a cause. It's just prediction. The second layer, it's the interventional one. Sorry, the second layer is the interventional one, where you actually have the interventional distribution, where the probabilities now are with this operator do X, in the sense that I perform an intervention on a variable X, and now I want to understand the behavior of the other variables. And in this case, we have machine learning models that can actually learn causality, for example, reinforcement learning. And this is just because you are actually doing some experiments while you are learning reinforcement learning. The goal from the graphical approach is to use some type of model that represents these mechanisms. So we could use, for the second layer, would be required it's a higher, or like a more, how can I call it? It's like it's encoding more knowledge than just the observation of distribution. That's why we need a graph to actually use this as a constraint for my model, and this is causal Bayesian networks. And with this, so with this type of models or this type of languages, we can answer this type of questions. That what would Y be if I intervene on X? So will my headache be cured if I take an aspirin? So I'm taking this action of taking an aspirin. I want to see the outcome of this intervention, of actually taking the drug. And the third layer is about counterfactual. Usually you need much more information about the structural causal model to infer counterfactual. Counterfactual is more about imagining or like suppose that you already performed some action. So for example, I already took an aspirin, and then I want to ask, was it the aspirin that stopped my headache? Like, what would happen if I hadn't take the aspirin? It's about inference in an alternative world. So usually it's more about individual inferences, because you need to imagine that I already did something. I, of course, cannot go back in time, so I cannot just collect the data for the same individual. So this would be a much more it's a harder question to solve, because you would need this information about the individual, and this would be called counterfactual analysis. I would just mention something related to the second layer. Maybe Frederick is going to talk about counterfactuals in the afternoon. So we will cover more the three layers of causality. So that's the goal. How can you move across these layers? So for example, how can you move from the first layer where you just observe data, or where you just have access to the observational distribution, and you want to infer something more about effects of intervention, so you can create some policies, treatments, and make decisions. So there is this theorem, the causal hierarchy theorem, that it's important for you to understand that we cannot just answer questions in one specific layer using information from a layer that's from a lower layer. So don't imagine that you can actually get causal effects in general. I would say, like, you see that some part some specific effects sometimes you can actually get just from data, but in general, you cannot get the true causal model or the true, so for example, you cannot get the true causal diagram just from data unless you have assumptions that are living in the second layer. So you need information from the second layer to actually infer causality. And those types of information can come in terms of assumptions of some parametric form, assumptions about the parametric form of the functions, or about the structure of the model. But you need more assumptions that live in the second layer to infer questions of the second layer. Or actually, you can have information from above. If you have the structure causal model, of course, can answer questions about causality, but you cannot do anything if you just have, you cannot, in total, you cannot have the true the information about the entire causal model just having data. So that's a result, unfortunately, but that's also exciting, I would say, because it's where maybe we can start working together to experts from the field. So that's where humans can enter in the loop and try to help our decision making in these algorithms. All right, I would just skip this, although it's a fun one, but for the sake of time, you just take a look later. It's a XKCD that I really, XKCD comic that I really like. It's about what's the difference between association and causation. So just read while maybe you can make the first and the second examples in our notebook. So we have two notebooks there, and the two the two items, the first two items in those examples are about constructing a structural causal model and then getting the induced causal diagram, and then checking the condition dependencies that are implied by the true causal diagram. I don't have much time, but and this is just basically run the code. I hope that you already installed the package. So those are the first and the second item. Maybe I can do with you. Reconnect. Hope that maybe I can just run this one. But the idea is to run the first item here, constructing the structural causal model and corresponding causal diagram. Yeah, I lost my internet, so I think I will have to install again. But I can show you locally. But the first, so I have a few functions that I'm providing to you, these helper functions. So the section helper functions, those are functions that I implemented. Basically, the idea is to construct a structural causal model. So that is this function, get BDSEM. In this case, I'm just manually constructing a structural causal model, so I know that's a linear model. And I know the order, so I'm just showing how can you, from this model, how can you construct in R. And the other function is, so this is just the true SEM, we get the BDSEM. Of course, I know the function, so I'm just constructing it. You can take a look in the function just to know how is this generated. And then later I'm getting the graph, which is also something that I can construct manually because I know the order of the functions. But you can read the functions and see how this is constructed using this package. So there are two packages that are important in causality. Most of them are actually in R. There are some wrappers in Python, but they don't have many functions available yet. So that's why I'm using R. The two packages that are more important, I would say, is the DAGT package and the PCAlg package. So that's the package that I'm using here. So if you run, you see, I'm going to run locally. Unfortunately, my connection destroyed my notebook. But I have here. So once you have, maybe you can try by yourself, but then we can see the output here together. Did you run? Yeah. So yeah. So the idea is to have like a graph where, I don't know, this could be larger. So where I have this connection A pointing to B and C, and D pointing to B, and D and C with a bidirected edge. So actually, this is being constructed in this function here. So I have the SCM just for later, but also, so if you see here the SCM, you see that this is just a set of coefficients. It's a matrix of coefficients. I'm just informing that the UCD is a latent variable. Also, the graph, if I plot the true graph with the U, would be something like this. So I have the UCD pointing to C and D. This is exactly the graph from the slides. Also, of course, we don't want to see this. We can use this iGraph library to just plot the graph with the bidirected edge. So this is just for the BD. I have another example. The other example is it's a bit more complicated, but we can see here that's a more complicated graph. And I'm not constructing the SCM. I'm just assuming that I have access to the graph. And then I can plot the graph with the bidirected edge. The libraries are not pretty. I have to say it. But the idea is to then infer effects from it. So, yeah, this is. So you see already that there is some confusion here, but this is like there exists a bidirected edge plus a directed edge. Those are just bidirected edges. This is just for you to have a reference. I imagine that you cannot use this for a paper or something like this, but the idea would be later to check the implied condition dependencies, and this is an important function to know. From the DAGIT package, you can see the implied condition dependencies, so just for this complicated graph, you see here all the implied independencies, all the independencies that are implied by this graph. So from the graph, you can check, for example, that X1, so X1 is here, is independent of Y2 here, given X2, and this is just because X1 is disseparated from Y2 given X2. So this is a path where X2 is a non-collider, so this path would be blocked. Is open, so I need to block when I condition on X2. And this other path is a collider here, so I don't need to condition on a Y3. And then, yeah, those would be the paths to be looking at, and those you'll be blocked, both you'll be blocked given X2. So that's why we have X1 independent of Y2 given X2. So you just use this separation on top of this graph, and then you have the implied condition independencies. But this function already gives to you the minimal condition independence. It's not all of those, but for every missing edge, you can get what would be the minimal set that makes the variables separated in the graph, and this would be the minimal condition independencies. Maybe I can also show for the backdoor. Oh, sorry, I'm already saying something, but I can say for the other graph, this would be so this would be just let me increase here. So A would be independent of C given B and D. A and C they are disseparated given B and D. Like when I condition on B, I block this path, but at the same time I open this triplet, so I need to condition on D to actually block the second path. So A and C are disseparated given B and D, and this implies the first independence here. And A and D are marginally independent because A and D are disseparated. This is just a collider in the middle. All right. questions? I already gave the break. I'm a bit late, but questions up to this point? No? I'm going to try to cover everything that I have here, so I'm going to maybe skip some of the examples, but of course we can discuss later. And the idea is to give you the graphical criteria that exist for effect identification, also to show the do calculus and then the ID algorithms. This is going to assume that you have the causal diagram as input, but later I also want to show some ways to relax the assumption of have the graph. So that's why I prefer to go faster in this part, and then we can see later what are the advancements that we have in the field. So the causal effect is just something that's derived from the interventional distribution, right? So imagine that I have a set of variables x and a set of variables y. So any quantity that is actually derived from the interventional distribution can be the causal effect for you. So for us, what's actually important is to infer the interventional distribution. And this you tell us how much y changes due to an intervention on x. So as examples in the field of what could be a causal effect, could be the average treatment effect. This is the ATE. So if I have like discrete treatments, I can just get one level of x prime, other level of x, just x, and get the difference between the expectation of y given to x. Notice that if I have the py given to x, or the intervention distribution, is just using the formula for the expectation. There's nothing hard to do. For continuous treatments, we can also use the partial derivatives. This is going to show the rate of change of the y with respect to the interventional y on x. Again, this can be derived from the interventional probability distribution. So, since there are many ways to define the causal effect, what the goal of these causal identification algorithms are usually to identify the interventional distribution instead of just infer directly the value of this difference. We try to infer the probability of y given to x, and then later you can do whatever you want. So that's the pipeline. You usually have a query as the interventional distribution, as I said. We will require as an input the causal constraints encoded in the causal diagram and a set of probability distributions. In this case, I'm just going to assume that you have the observational distribution. There are some extensions of this algorithm where you can combine multiple interventional distributions as well. And the first implementation of this algorithm was by Jin Tian and Pro in 2002 in this paper. And what the algorithm can tell you is basically if the set of constraints that you have encoded in the causal diagram plus the distributions that you have available are sufficient actually or not to get an expression for the query. The query is just the interventional distribution, so the py given to x. But this expression has to be just in terms of what you have available, which is just the observational distribution in this case. So you see here that in the right side, I have no do operator. It's just terms referring to conditional probabilities. And so identification means that I can actually do a mapping from the available distributions to the interventional distribution. So using what you have available. That's why you can actually move across the layers of the Pearl's causal hierarchy when you have identifiability. You can move from the observational layer, which is the layer 1, to the layer 2, which is the interventional distribution. Note here that you require structured knowledge. This has to be available. I'm going to skip this, but maybe just quickly, I'm going to say that identification means that doesn't matter what's the model that you have that is actually agreeing with the graph and the probability distribution. Could be many, as we discussed. There are many models. Of course, the true one is among them. But if you just give me the causal diagram and you have access to the correct probability, the correct observational distribution, then doesn't matter what's the true model here, it could be unobserved, you collapse to just one interventional distribution, which means that all those models that are agreeing with the graph and the observational distribution, they have the same interventional distribution. That's a collapse, it's a very specific case where you have collapsibility. And this is where we call identification. So in words, a causal effect identifiability means that no matter the form of the true SEM, for all models that agree with my graph and my observational distribution, they are going to agree with the probability of y given to x. So we have like different, so considering all the space of all the models, we have those that agree with the, in blue here, they agree with the graph. In yellow, they agree with the probability distribution, the observational probability distribution. So if in the intersection, all of those have the same probability of y given to x, then we are in the identifiable case. But if there is at least one model that you can show that the effect or the interventional distribution is different from another, then the intersection has some models here that they have a probability of y given to x that's different from the others, then you have a case where the effect is non-identifiable. So we are looking for these situations. You can only infer a causal effect when you have identifiability from the causal diagram and from the observational distribution. So notice that even having the causal diagram, it's not always you have a causal effect. Right? It's still unclear because of this class of models that are compatible with the graph. So tools for causal identification. So we can separate the tools according to the graph, to the case that if the model is Markovian, which means that there are no unmeasured confounders. So those are simple adjustments that you can do. In the case where you have no unmeasured confounders, actually all the effects are identifiable. So it's kind of easy, this setting, because you can directly go from the graph, so without running any algorithm, you can just apply the adjustment and this is going to work. In non-Markovian models, you need more tools. So these tools include the backdoor criteria, the generalized adjustment criteria, the front door criteria that is going to give you the identification through adjustment. Also, we have the do calculus, so it's just a calculus that's going to allow you to operate with interventional distributions. So now, remember, now you have to see if there are independencies between the do x and the variable. So that is like how can you detect invariances between the interventional distribution and the observational distribution, so you can remove the do's. Then you need in the end, so we combine all this stuff, we can have a complete algorithm. We have this identify algorithm or ID algorithm that's complete in the sense that if you have an answer from it saying, yes, your effect is identifiable, this means that it's sound in the sense that your effect is going to be the same in every model that's compatible with their graph and the probability distribution. But if it says that it's not identifiable, you are certain that exists a model that's compatible with the graph, that the probability of y given to x is different. So it's complete, like you can just run it and get a formula in the end. So those techniques are all available in the book, the Causality book by Pro. So that's why I said that if you read that book, you know a lot. But the ID algorithm is in the thesis of Jin Tian. So the identification in Markov models basically just follows the truncated factorization. So the probability of y given to x, the probability of v given to x, so the entire set of v given intervention on x, it can be factorized by the parents of the variable in the interventional distribution. So this just follows directly from the property that the distribution actually follows, agree with the structure of the graph. So we call this Markov property. So you can actually have, you can just, every variable just depends on the parent. So again, this is Markovian case. And another property that's important for Markovian models is that we have something that's called modularity, where you can actually remove the intervention on X. Sorry, I think I have to specify this notation here. So sometimes we put the X as a subscript. This just means that there is a do X. So these are these two different ways of denote the interventional distribution of V given do X. So either I put the do X here or I put the X on as a subscript. And this distribution factorizes according to the graph. And another thing that happens is that the intervention on X, given the parents, is independent of the variable. This is called modularity. So it doesn't matter. So once you intervene on, once you observe the parents, you can make interventions on any other variable in the graph that isn't going to affect, because you already observed the graphs, the parents. And because of this, this leads to just this formula. So that's called G-computation by the Robbins framework, but it's just the truncated factorization. Like you can just sum over all the other variables that are not X and Y and get the probability of Y given to X. So this is just the probability of V given to X. Of course, you can marginalize all the other variables and get what you have, what you want. That's the probability of Y. But it's kind of, this works for every graph, because you never, you are under this Markovian case where you don't have bidirected edge. So you can just apply this formula for any Y, any X, and it's going to work in Markovian models. So this is just an example. So there's no bidirected edge here. So from this graph, I have the factorization over the parents given, the variables given the parents. In the interventional graph, basically, I don't have the term for X because X is just fixed, but every other variable can be factorized as the variable given the parent. So there's no parents in the Z. Y has parents as X and Z, so those are those after the conditioning bar. So this is the probability of V. V is just Z and Y. And if I want the probability of Y given to X, I just marginalize over Z. So it's pretty simple. It's just applying this formula, this truncated factorization here. Another criteria that we have for Markovian models is called adjustment over parents, but it's just it follows direct from the truncated factorization. So you can always apply this. So instead of using the truncated factorization, you can also apply this formula. So in this formula, you have you just need to condition. So there are two terms. So it's the sum over the parents of X. So you just need the parents. So in this example, the parents of X is Z1 and Z2. And you can blindly say that, okay, I don't need to check the truncated factorization. I just need to check who are the parents of X. And the parents of X are going to be here in the sum, also in the first term. So it's probability of Y given X and the parents of X multiply the probability of the parents of X. So this formula gives you directly the interventional distribution. It's called adjustment. And it always works if your model is Markovian. Questions related to Markovian? But in semi-Markovian, so in the case that you have unmeasured confounders, this is complicated because first, the truncated factorization, you be this one. And in this one, you see that that is I need the parents of the variables, and the parents of the variables now are the U variables. Those are creating confounding. And I cannot get rid of these U's. I cannot condition on the U because U is an unobserved variable. So this formula is not helpful at all. Like I know what's the factorization. If I have the U's, I can write it. But of course, I don't have the U, so I cannot use it. So for semi-Markovian models, you need more advanced tools like these graphical criteria that we are going to see, because we need in the right side here an expression that's completely free of the U variables and also of the do operators. We cannot compute this. So the first criterion is called backdoor adjustment, and this backdoor adjustment tells us that if that exists, so let's assume again that X is my set of treatment variables, my Y is my set of outcome variables, and if that exists a set Z that blocks, now I just let me go directly to the graph so we can follow easily. So the first condition says, so I want the effect of X on Y. I just need to look at the paths that are into X, paths between X and Y, but there is an arrowhead into X. Those paths are called confounding paths or backdoor paths, and those creates confounding. So every time that you have a path that's into X, you are not certain that the association between X and Y are actually due to the directed path. Could be just due to this path that's creating a confounding. So you need to block these confounding paths. And to block, you need a set Z. So through the separation, we need to find a set Z that blocks all these paths. But there is also a condition. The set Z cannot have descendants of X. So this variable Z is not a descendant of X, it's a parent. So descendant would be something that has a directed path from X to Z. So this is not a descendant of X. And you see that this path can be blocked if I just condition on Z, because it's a triplet that's a non-collider. So the set Z equals to the variable Z actually satisfies my two conditions of this criterion, because I block the backdoor paths, the variables are not descendants of X. And in this case, I can apply this backdoor adjustment. And look, this is very similar to the other formula, the adjustment over the parents. But then instead of looking at the parents here, I look at the variables on the set Z. And the set Z many times are just called as the covariate sets, because usually covariates are pre-treatment variables. So if you have like a set of many covariates in your data set, if the set of covariates blocks all your confounding paths, it's a very big assumption to say this, because you need to check you need to know the graph and then check for every path if the set Z is actually blocking everything. But if you have this, then you can automatically go directly to this equation and compute the effect of X on Y by computing the interventional distribution. So that's kind of the easiest criterion that we have in the field. Note that it's not complete for covariate adjustment. That is this graph here. Basically, you can see that there is no way to, there are two variables X and one variable Y, and we would like to have the probability of Y given to X and 1 and X2. So we would have to check every confounding path between X and Y for every X. So that is this confounding path, that is this confounding path, and that's all, these two confounding paths. But you can check later that there is no way to find a set that has no descendants. You first see that Z1 and Z2 are descendants of X1. So to start, I cannot use the Z's. So I cannot even block the first confounding path between X2 and Y. So this shows an example where the backdoor criterion doesn't work, but still the effect is actually identifiable by adjustment. And so it's not complete. It's sound, of course, the backdoor criteria, it's sound, but it's not complete. And we will need descendant, for this case, we will need to adjust over the Z1 and Z2 to work. And the set Z is Z1 and Z2. And then this Z1 and Z2 is actually violating the condition of being descendants. Actually, that is the adjustment criteria. So that's our second criterion for identification that was proposed by Spitzer in 2010. Basically we can let me try to go quickly over it. So basically, we need a new definition that's about proper path. So a proper path is just a path that is not going to be over the variables x again. So, for example, the variable x1 to y, I have one. Causal paths are just paths that are directed. So x1 to y, I have two causal paths. This direct edge is a causal path, right? This one. But from x1 to y, I have this second other path that's a directed path, but it's through x2. And there's also this other causal path. And the first two paths are proper causal paths because I don't have any x variable in the middle of my path. But the second path, this from x1, z2, z1, z2, x2, and y, it's called non-proper causal path because I started with an x variable and I passed through another x variable. And this is a problem. I don't want to look at this non-proper causal paths. We could use the same definition to get the non-proper non-causal paths. So non-causal paths are any path that are not directed. So this path x2, z2, and y is a non-causal path, and it's also proper because there is no other x in the path. But this path x2, z2, z1, x1, and y is non-causal because it's not directed, but there is x1 in the middle, so it's non-proper. So it's a non-proper, non-causal path. So given this definition, actually we have the adjustment criterion for ADMGs, and basically there are three conditions. The first condition, let me go, there are two conditions actually. The first condition just says that I need to block just the proper non-causal paths between x and y. So I just need to look at the proper non-causal paths between x and y and check if they block. If they are all blocked by a set Z. And then in the set Z, the only problem is that if I have descendants, so I cannot have descendants of Z that are lying in a proper causal path from X to Y. So I can allow some descendants as long as the descendants are not lying in a proper causal path from X to Y. Basically, and also cannot be a descendant of a variable in a proper causal path. So in this example, and then if it satisfies, we will have the adjustment formula as you saw before. So in this example, the non-causal paths, the proper non-causal paths between x and y is just x2, z2, and y. So x2, z2, and y. This is a non-causal path, and it's proper. The others doesn't matter. And the proper causal paths are just x1 and y and x2 and y. The other is non-proper, so I don't need to look at them. So I kind of just need to find a set that the variable is not lying on this path, on the causal path. So I cannot use x1, x2, and y. Okay, that's good. But then I can use z1 and z2. So that's the example that we saw before. And as long as I have a variable, either z1 and z2 or both, that's blocking my only non-causal path that's proper, I'm fine. So in this case, the empty set doesn't work because I have this path that's open. But the set z equals to z2 also doesn't work because this path is blocked, but then I have to look at this path here, and this path is a proper non-causal path that's open now with this collider. So x1 to y would be opening by conditioning on z2, but then I have z1 and z2 that would work. So x1 to y, I have actually this other non-causal proper path because it's non-causal since there is a collider here, so it's not a directed path from x1 to y. And conditioning on z2, you see that this is open, but then conditioning on z1 actually works. So z1 and z2 are actually satisfying my adjustment criterion for this graph, and I can use the adjustment. So I can just apply this formula where z is equal to z1 and z2 and get the probability of y given to x. when we have adjustment, we have, so every time that we have a set that satisfies either the backdoor or generalized adjustment, we will have this formula as we saw it, but we can actually make a trick here. And this trick is the following. So this is just the adjustment for all these criteria that we saw. We end up with the same formula. So those are called adjustment formula. And this is one graph where this works. Just pick the z equals to the variable z, and this is going to work. And we can do the following trick. This is, so you can see that the joint of, just multiply first by p of x given z. So this is just multiplying by 1, right? You can do this. There's no problem with this. And then you can see later that this factorization in the numerator is just by the chain rule. You can just put them together and convert this to the probability of y, x, and z, right? So just putting together by the chain rule. So in the numerator, you'll be the joint of p, y, x, and z, and the numerator now is going to be this new density here, is the density of x given z. And this numerator is called propensity score. And you see, I guess, with Frederick later, some algorithms that help you to estimate the propensity score and do this very efficiently. Like this is called the propensity score estimation. So how can you estimate from data the probability of y given to x when you have adjustments? So if you are certain that this is working, that you can do the mapping, either because you have backdoor or adjustment, or you apply the backdoor or the adjustment criteria and it's working. You can actually directly apply these propensity score ideas where you efficiently can compute the probability of y given to x. Note here that in some other fields, this condition where the backdoor formula is being satisfied is called condition ignorability. If you are familiar with the potential outcome framework, you will see that this is called condition ignorability, and is just sometimes is denoted by the independence of the outcome and the treatment given the set of covariates. Yeah, so that's a case where you can use also I think Frederick is going to explain better, but that is this inverse probability weighting and propensity score approach where we can actually estimate this very efficiently. So what if covariate adjustment doesn't work? Then we have other criteria. So the other criterion that's really famous is called front door adjustment. So in this front door adjustment, you are not looking for a set of covariates, but you are looking for a set of mediators. So we are going to call it M. And there are three conditions to satisfy them. So the set M needs to intercept all the directed paths between the variable x and the variable y. Also, we cannot have any backdoor path that's unblocked given the empty set between x and M. And also, we cannot have any unblocked path between M and Y, but now given the set X. You see it in an example. And if this is following, if these three conditions are satisfied, then we can use this different formula. So it's a completely different formula to estimate this. You ask me later. It's going to be hard. But then it's another formula, and it works, for example, for this graph. So you see that in this graph, x and y, there is a confounder, a hidden confounder between x and y. So I cannot even try to find a set z that blocks my all confounding or backdoor paths between x and y. So I have the alternative in this case to use mediators of x and y. And the set M equals to M actually blocks, intercepts all directed paths between x and y, because I have only one, so it's intercepting the path. Also, I don't have any unblocked backdoor path between x and M, so there's no path here other than, so from M to Y, from x to Y, M, from X to M, I have two paths. So that is this one, but this is blocked, and this is just the directed. And the third condition is the path is between M and Y. So between M and Y, I have this path here, but it's blocked by X. So as long as this path is blocked by X, and then I'm fine. So in the case that M is equals to the variable M, I'm satisfying the front door criterion. Look here that there are others. Well, so this is a case where the M1 and M2 would be required because we need to intercept two paths. If I have a directed edge from X to Y, this doesn't work anymore because I don't have a variable intercepting this directed path. Also, if I have confounding, as I told you, this would be a violation of one of the conditions. This doesn't work. So there are still graphs where this doesn't work. And to be honest, there are many scenarios beyond backdoor and front door. Like there's even some graphs that have names. So there is a conditional front door. The formula is again different. The napkin is another graph. The formula is again different. There are other graphs. There's no even name. Like you can give your name for this graph and just get another formula. I mean, there are many, many graphs. So how can you actually perform infer effects in a general way? So we have a calculus. This is more educational, I would say, because it's just three rules. It's a set of three rules that allow you to convert or detect invariances. Like, for example, in the first rule allow you to check independence of X and Y in the interventional distribution under the do-W. The second one is the independence between, not independence, but it allows you to remove the intervention on X so you just change an intervention on X to an observational on X. So in this case, observing the value of X is the same as performing an intervention on the value of X. And this can be checked by a particular separation on a manipulated graph. So that is these manipulations that you can apply in the graph. So when you have a bar, you are removing edges into the variable W. And when you have a underline X, in this case, you remove the arrows out of X. I'm going fast here because I'm going to skip this part, but the idea is that there is a set of three rules. The third one is independence, completely independence of the intervention X on the variable Y, so you can remove the do X completely. So you can actually applying this rule, you can do operations on top of the probability of the intervention of probability, and the goal would be to remove all the do's. I'm going to skip this. You can check later. There are several examples. But this is a nice example that shows how you would derive the front door criterion from the rules. So you start, for example, from the probability of Y given to X, and then you see that you have do here, you have do here, but you can start applying the rule 2, the rule 3, some probability axioms, and then in the end, you actually have a formula that's completely do-free. And in this case, you have identifiability. Another break? Yes. Just to conclude this part, so in the end, we don't use the calculus in general. The calculus is more educational because it would be like really hard for you to derive every time applying the set of rules until you don't have any do's anymore. So we have an algorithm. I won't go over how can you actually understand every step is in the algorithm, but the algorithm, you just give a graph for this algorithm, and then in the end, it is going to tell you if it is identifiable or not, and that is a formula. So that completes our pipeline. There are many more. You check later. There are some references. Okay. There is this slide that I put some references, and the last one here is about one recent work by Kevin. It was in the lab of Elias Barenboim as well. That's called the causal neural connection. So I think that was the first attempt to actually how can we leverage the power, the expressiveness of neural networks to do causal effect estimation and identification actually at the same time. And I want to just give a few intuition about what's there in this paper, because maybe you are interested in this part. And it's related to this part of the lecture where we are assuming a causal diagram. So in this work, basically, we know already, so we assume that it is a true causal model, but we don't know it. But we assume that you have access to the structure of it, a causal diagram. And the way that you can leverage causal deep neural networks is to create a neural network that we call a deconstrained neural causal model. It's basically, for every edge in the graph, you are going to create an architecture that's going to receive as input the parents. But one additional thing is that the U variables, those that we don't observe, we need to create some artificial variables for them. So for every click, a bidirected click, so for every variable for every set of variables that are connected by bidirected variables, so for example, X and Y, they are connected by a bidirected edge. So this forms a click. And I will need to manually construct a variable U that is going to be a uniform between 0 and 1, can be anything, to be honest, but let's just pick something simple. And then you kind of use this as a parent. So in our graph, this UXY, which wasn't observed, is going to be simulated as a variable that's uniform between 0 and 1. And this is going to be parent of the is going to be input of the neural network that determines the value of X, and also is going to be input of the network that determines the value of Y. And this network also receives the mediator, in this case, as is also parent. You also put some U variables, so a variable that's disconnected, like the Z variable, is forming its own click. So you need also the UZ, that's a parent of the Z, and then both variables are going to be input for the network that generates the value of Z. So that is just like a way to create, like is to induce, actually this is called inductive bias. So how can you induce some structure in the end, in the model that's going to be estimated in the end? So we enforce these constraints. And the idea is the following. We know that the true causal model, it induces the probability distribution, the 3 layers of the Proust causal hierarchy. So we have layer 1, layer 2, and layer 3. And the model also induces the graph. And then using this constraint approach, we have a model that's going to at least agree with the structure of the graph. By training, we can actually make sure that the observational distribution is matching between the true causal model and the one that's going to be estimated in the end. Just is what we have been done so far. So it's just how can you get the best observational distribution? How can you estimate the best observational distribution from data? And the first question is it always possible to infer something like that's going to be needed for our interventional distribution? So suppose that we have a query that's the probability of Y given to X. So this corresponds to a pair of variables, right? So there is one effect only. And we know a priori that this is identifiable because it's the front door graph. But we won't need this. We won't need to know this information. But in this case, I know that the neural network is going to be able it's going to have the expressiveness to actually estimate the observational, the probability distribution in the layer 2, which is the interventional distribution. It has this expressiveness. So that was proven by this in this theorem. So for any SEM, doesn't matter what's the true SEM, you don't know it. You don't even know how to specify it. But you know that the neural network that actually agrees with the graph has the power, the expressiveness of estimating the probability distribution in the 3 layers of the Pro's causal hierarchy, including the interventional distribution. Note, however, that we are not saying that the model in the end is going to be the true one. We are just saying that there is the expressiveness. Then there is the second trick here. So in the algorithm, what they do, I'm going to just parse very, very quickly, but that is in this lines 2 and 3, you at the same time minimize, so there are 2 optimization procedures. The first one, you minimize the causal effect, in the sense, in this case, it's just the probability of y given to x. That would be, so you can actually do this because you have a model. So you are feeding a model using a neural network. So in this model, you can manipulate it, and then you can compute the effect of x on y, just applying the manipulation on the model. That model, I'm not saying that that's the true one, but the estimated one. And I try to minimize this effect. So I run a procedure, optimization procedure there. And separately, I also run the maximization of the same probability of y given to x. And as I told you, identification we can only have identification when doesn't matter what's the model that I'm feeding, or the model that agrees with this graph and the probability distribution, the PV, the observational probability distribution. Doesn't matter what are the models. They are going to agree with the same interventional distribution. In this case, just the PY given to x. It's just one effect. It's just one edge. So what they do is a check. Is the maximum and the minimum the same? If they is the same, which means that the range of like all the possible causal effects among all these possible models that are agreeing with the graph and the observational distribution, they are the same. You collapsed the effect. And in this case, you have identifiability. So it's a new way of identifying the causal effect through optimization procedure. And then since you can get any model of the class of models that are agreeing with the graph and the observational distribution, like since I said that doesn't matter, you can just get the one that was estimated to get the effect of x on y. But you can only say, so that's what's saying here. So Q is going to be identifiable if and only if they match. And the query is going to be, if the query is identifiable, we can just perform the mutilation in the estimated model, which not necessarily is the true one, but at least for that specific causal effect, the x on y, I can use this model because it doesn't matter the model. It's a bit constrained because I can only tell what's the effect of x on y. And I'm just using the neural network for the expressiveness of it, just to estimate better the effect in the end and at the same time getting identifiability. This doesn't give you complete explainability yet because I'm just saying doesn't matter the model is not even the true one, so it's just a technique to actually allow you to estimate and infer the effect at the same time. All right, I'm going to ask you to do the examples just in the end so we can actually see what I prepared for this last part of the tutorial. But the example 3, if you even want to do this now while I'm continuing the lecture, but maybe let's just keep this later. I'm showing how to do the identification through adjustment and through the ID algorithm for these graphs that you created in the beginning. This is using the function GAC, Generalized Adjustment Criterion, that's available in the PCAlg package, and the ID algorithm is available in the Causal Effect R package. So if you want, you can run, but I'm going to just continue the lecture, and then we can just do the exercise in the end. So I want to move to this part because many people ask me how can you get a causal diagram? This is already very hard. And that's the point. So I've been working exactly on that. What I mean is that it's usually hard to get this graph, right? So what are the alternatives? What we can do? That's just the question. Is it possible to relax the assumption of having a fully specified causal diagram and still be able to identify the causal effect? So one work that I actually, a recent work, it's about how can we still create a causal diagram even though you have like just a partial understanding of it. So suppose that you have a set of variables, this A, B, C, D, X, S, and Y, and you know kind of that X points to S points to Y, but you don't really know what's the relationship between all the variables A, B, C, and D. Like you don't know what's happening there. Could be anything. However, you can, so using what you have, what I told you so far, it's not possible to create a causal diagram. You are stuck. So how can we identify the probability of Y given to X in this case? So one approach is to create like something that we call cluster DAGs or cluster causal diagrams. You start with a partition. This partition exactly tells you the set of variables where you understand the relationship across the sets of variables, but you don't know what's happening within the variables in the cluster. So for example, I know what's happening between X, S, Y, but I don't know what's happening between the variables between A, B, C, and D. And then you can construct a cluster DAG by considering the cluster as a unit, like basically. So it's kind of the same procedure as before. But instead of having every variable, we are going to have every cluster. So we will have now an edge that goes from a cluster to another if it exists at least one variable in the cluster. So from all the variables in the cluster, if at least one of them could be, now it's a potential cause, could be a cause of X, and this could be through a directed path, doesn't need to be even through I mean, it's going to have one, but if you have at least one that has a directed edge from A to X, then you add the edge. So for example, and the variable itself can be a cluster, right? So we know that X, this comes from prior knowledge, so you could say that X points to S points to Y, but then one of these variables points to X, and one of those variables doesn't need to be the same, points to Y, as long as you believe that could exist, you create the edge. And for the bidirected edge, is the same thing. Like instead of doing variable by variable, you do this cluster by cluster. So if at least one variable in the cluster could be caused by a variable that's unmeasured, but could be caused by this variable, and also X could be caused by this one, which means there is an unmeasured confounder between the cluster and the X. I will have to add the bidirected edge between the entire cluster. Anyways, could be for the other as well. Like it doesn't need to be the same variable, but as long as there exists at least one, you have to add the edge. This is going to assume the same assumption as before. So the graph over the clusters cannot have cycles. So depending on the partition, you would be able to create some cycles. So if you do this case, basically you need to collapse the clusters until you don't have the cycles anymore. So this actually it comes from the fact that you don't know, you don't have enough knowledge to create this partition. We can discuss this later. So what is actually a cluster causal diagram? It's basically a representation of many diagrams at the same time. So for all possibilities of orientations among the variables within the cluster, this actually allows you to have any configuration of relationships amongst the variables within the cluster. So this is a class. So this could be one member of the class. This is another member of the class. Like I'm agreeing all the time with this structure because there is always a variable. So the direction is always following. Like I cannot have X being a cause of these variables in the cluster, because otherwise this would create a cycle. So as long as I'm having the same orientations and having confounders between the cluster and the variables, I actually can have many modules that are compatible with it. And the identification actually would be, can we identify for the class? So instead of picking one of them and assuming that this is the true one, we would have to now consider identification for the whole class. We were already talking about classes of modules with one diagram, but now we are talking about classes of diagrams, which is like a much larger class. The idea is that you have now a flexible encoder of this module assumption. So if you have the knowledge to actually create the DAG over the diagram over every pair of variable, you should do it because you should encode as much knowledge you have. But if you don't have it, you can just start creating these clusters, and then, of course, if you have no knowledge at all, you would actually end up with just one cluster, and from this one, you wouldn't be able to identify an effect. So that is like these bars saying that the inference power and the model construction, they are kind of going one against of the other, so you need to find a trade-off here. So I told you already that this is just manually created by depending on the lack of knowledge or communication, and this is good for communication. But the point is, we extended everything that we had before for DAGs or common causal diagrams of variables. This now is extended for cluster causal diagrams. So, okay, you don't have knowledge for all the pairs of variables, maybe you can have this. It's relaxing, at least a little bit. So the idea is the same. If you have identifiability, you have identifiability for every graph in the class. If you don't have identifiability, at least one possible diagram in this class, you would have the effect non-identifiable. That's why you don't have identifiability for the whole class. And this doesn't need to be the backdoor. As you said, you can apply any criteria that you have, and even the ID algorithm. So what if we don't have knowledge at all, right? That's another question that some of you ask me. So can we learn a causal diagram just from data without any prior knowledge? Yes, kind of. We have like something that's called causal discovery in the field. The point is you cannot learn one graph, but you can learn again a class. So it's a class of all possible models that agree with what we observe from data, which is a set of condition dependence relationships. So again, we cannot do identification on this class without extending the tools. So, I think I have a few minutes. I will explain just the big picture of what causal discovery does before moving to identification from this, using this class. But we have now identification on top of this class. So causal discovery is going to just use what you can observe from data with condition dependencies and independence. And the classical algorithm is the fast causal inference, or FCI algorithm. So in the exercises, you're going to run this algorithm. And it just depends on data, nothing more, right? So what the fast causal inference, or FCI algorithm, do? Basically, the goal is so we are going to assume 3 assumptions. So I'm going a little bit fast here, but there are 3 assumptions. The only thing that we want is that there is a match between what the graph that I'm going to estimate is going to represent all the entire set of condition dependencies that I observed in the data, and everything that I observed in the data, I have to assume that's what actually was generated by the true model. So so basically there are these 2 assumptions. One is called Markov or semi-Markov condition. The other is called faithfulness condition. But the point is that is a match between what I have in the data and what the data generating process actually created. To do this, to extract the set of condition dependencies, I will need additional assumption, which is a condition independence test. There are several condition dependence tests available. Some of them you have to assume some type of parametric form, or at least assume some distribution for the variables. Others are completely non-parametric. There are several packets available. You can take a look later. Those are several references, but there are many more available, and you need this test to run the algorithm. The idea is the following: like, you have data. This data actually can be generated by many models, as I explained before. And from data, you can actually get just a set of condition dependencies, right? Dependencies and independence. That's the only thing that you can actually extract using a condition dependence test. And the point is, you can try to manipulate the joint distribution as much as you can by applying this independence, trying to simplify and stuff like this, to actually get a Bayesian a graphical model or a Bayesian model that actually just fits to this data. But there are many. It's not only one. And this set of all these graphs that are actually representing the set of condition dependencies is creating a class that we call Markov equivalence class. So any model in here, it represents perfectly the set of observed condition dependencies that we have in the data. However, in this example where X is independent of Y and you have these other dependencies, you can see some invariances sometimes. So all these models that you see here, you see that the Z variable is always a collider. So there's a collider here. Actually, I can even do this. And you see that every time in every model, Z is a collider. And even considering the measured confounders. So the causal discovery algorithm, or the FCI algorithm in this case, is going to detect all these invariances, all of them. Every time that the edge is the same across all these models that we have in the class, it's going to learn. This is a complete algorithm. So you would have, in the end, a representation of the class, where you have the edge mark. Every time that you have an edge mark, either a tail or an arrowhead, you have an invariance. And every time that you have a circle, it's because it could be one or the other. And that's actually the flow. So suppose that I have this graph as the true one. Of course, I don't know it. The idea is to start with a complete graph. So the complete graph has no information, basically. But I apply the condition dependence tests. And for every independence, so of every pair that I could find a set that actually makes X, the two variables independent, I'm going to remove the corresponding edge. So for example, X and W, I remove the edge between X and W. Or X and Y, I remove the edge between X and Y, right? Because I found, so it's not associated directly. And then there are a set of 10 rules. I'm not going to go over it, but it's in this paper by Jin Tian, 2010. So he actually showed the completeness of the algorithm by applying this the set of 10 rules. And then in the end, you have all the invariances that are possible to have. So, for example, in this case, I can even know that W is a cause of Y, Z is a cause of Y. Oh, sorry, yeah, Z and W, they are both cause of Y. I could learn just from data, because it's an invariance. That doesn't matter what's the graph that would actually fit to my data. This is happening in all of those. And this is in green because we have a property called visibility that even tells us that the edge and the edge it's not even confounded. There's no confounding happening there. So you actually have a true cause that is possibly going to be identifiable later. This graph is called partial ancestral graph, and it's called ancestral because the associations here are actually indicating ancestrality, not direct connections. So I don't have here in this example, but Z is a cause in my example, but Z could be just an ancestor of Y through a different path. So you cannot just get this edge in the graph and assume that there is a direct cause. It's just that there is a directed path or a causal path, but it's still a cause. You just don't know if it's direct or indirect. So the interpretation is the one that I told you. So arrowhead, they mean no ancestrality. So for example, Z is a known ancestor of W. Tail is an ancestral relationship, so Z is ancestral to Y, and circle are just known invariances. I also can learn spurious association, so sometimes I can have like bidirected edges. The meaning of this is not just one unmeasured confounder, it could be yes, any inducing path that it's not direct path. So, but the only thing that I know is that A is not an ancestor of B, B is not an ancestor of A, so one is not the cause of the other. It's just a spurious association happening there. And it also can have, it can even detect some association due to selection bias, which will be represented by undirected edges. Okay, so I'm just listing here a few graphs, so you can take a look later, but this would be the underlying causal diagram. Of course, we don't know, we would have just data, right? And this would be the corresponding peg or the partial ancestor graph that we would be able to recover using the FCI algorithm. So you see here that there are cases where there are several circles, but it's still other graphs we can learn, like completely spurious associations or ancestral relationships like this one. This is an example where I told you that you see the Z is pointing to Y. It's a direct edge, but in the end, in the beginning, Z is just a cause, it's an indirected cause. So it's not in green here because this could be confounded, but it's still Z is a cause of Y through another path, and this is captured by the algorithm. And identification, so the question that now is important, can we do identification from a peg? And yes. So for covariate adjustment, Perkovich in 2015 and then in 18, so she has this last paper about it. She actually, together with others, they extended the covariate adjustment, the one that we saw it, to equivalence classes. So you can apply this, the same criteria, so you have to extend a few concepts there. And also recently we proposed this complete calculus and algorithm that can actually identify marginal and conditional causal effects from pegs directly. So it's a completely data-driven way of doing causal identification. So this is in this paper in the RIPS 2022. I mean, we actually, so in the end, we actually relaxed the input, the second input here, instead of having the peg, we have the DAG, or the causal diagram. We have an object that's completely learned from data. So it's representing many models. It's possible that in the end you can have a positive solution, right? So there is the adjustment criteria. There's the other algorithm that we developed is available in my GitHub here. So you can download it. It's part of the list of exercise. But these algorithms, they can take as input the peg and tell you if the effect is going to be identifiable or not, just giving the object. And I mean, this is just simple soundness and completeness. Like, I mean, it means that every model is going to be identifiable if it is identifiable, and if it's not identifiable, that exists at least one that's not. So in conclusion, so causal inference can help overcome critical challenges in artificial intelligence, so including robustness, generalizability, explainability, and fairness. It provides, so I think the goal of causal data science is to provide like a language to actually combine data and knowledge at the same time. So it's not only data, should not be only data, or it should not be only knowledge. It should be a way to combine both. And the goal is to investigate causal explanations, to have explainability, and to give you a better way to do decision making. I believe that these recent developments for causal inference is actually helping to bridge the gap between the practice and the theory. Hopefully you also can do this with your work. If you have like any questions, we can just discuss later. These examples that I told you that are there, so we are going to just do the causal discovery using the FCI, and then you can check that the condition dependencies that are implied are exactly the same, so it's always preserving, so the object actually preserves the set of condition dependencies, and you can do effect identification from a PEG using the algorithm. So thank you so much. So just ask me questions, could be now or later through email. Thank you.